All right, we are starting a new idea this week. We're going to be looking at how to expand binomials, called the binomial expansion. And we're going to focus on using the method of using Pascal's triangle. This is what I mean by that. When you have a binomial, either squared or cubed or to the fourth power or whatever power, there's this cool method using Pascal's triangle that makes doing these sometimes very complex tasks, it simplifies it. This is what I mean. So here's Pascal's triangle, and I don't know if anybody else notices, but in case you forget this order, at least up until this level right here. So look at this right here. That is 1, 1, and this is 1, 2, 1. And what I know, and 1, 3, 3, 1, what I notice is those look an awful lot like the powers of 11. So this would be 11 to the 0, 11 to the first, 11 squared, 11 cubed. And once you get beyond this on most calculators, it starts, because we have double digits, it won't look like this. But up until this level right here, if you plug into your calculator 11 to the fourth, it will give you this. So you could actually build Pascal's triangle using your calculator, and then after that, then it's pretty easy to figure it out. Because if you notice, this level right here, 0 plus 1 is 1. 1 plus 0, that invisible 0. That's why on the outside, all of them are 1, because then again, on this next level, 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 0 is 1. Next level, 0 plus 1 is 1. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 0, 1. 0 plus 1 is 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 0 is 1. So forth. So I hope you notice that pattern. But this is what I also want you to notice. Just like this is 11 to the 0 exponent, this is a binomial to the 0 exponent. The level that's 11, just like that's 11 to the first, this is just a binomial, x plus or minus y to the first. When it's 11 squared, you're going to have a binomial squared. When it's 11 cubed, a binomial cubed. 11 to the fourth, so forth. So that's how that works in case you forget. All right, then here is some things that you need to know. Pascal's triangle ends up being the coefficient. So when you square something, remember when you square this, let's ignore this for a second. When you square that, x times x is x squared. X times y is xy, but then y times x is xy. Oh, look there's two of them. And then y times y, well, look at what you have. You have 1, 2, 1. So Pascal's triangle over here ends up being the lead coefficients for the terms. But then there's this other stuff. This is x squared. This is x to the first. Oh, that's y to the first. And that's y to the second. So not only do we have Pascal's triangle that tells us the lead coefficients, but it also says, hey, we need to put things in the first term is going to be in descending powers. So x squared, x to the first, x to the 0. The second term is going to be in ascending order of powers. So it'll be y to the 0. There's this y to the 0, y to the first, y to the second. So this is how you could show that. So according to this right here, we're going to have 1, and then we're going to have descending. So x squared, y to the 0. Then we're going to put a plus sign. Here's the lead coefficient. 2, Well, there was x squared, so now it's x to the first. There was y to the 0, y to the first, then a plus sign, and then we have 1 again. X squared, x to the first, x to the 0, and y to the second. And notice I have the x to the 0 and the y to the 0 kind of not very visible. It's because any non-zero number or variable to the 0 exponent is just going to be 1. So those can actually be invisible. And there you have the final result. All right, let's try one really quickly. Let me look at the time, and I might stop it right there. Okay, I'll stop it there, and then for an example, we'll do